So, and now we would once again share the screen. So, once again, I would like to repeat that previously we discussed about the meaning of the intercept in the model with no independent variables. And we have discovered that odds ratio for the intercept is the ratio currently for those who didn't survive divided by those who survived. Or in logit scale, it was 0.651, and its odds ratio, it was approximately 2 divided by 1. We can take these values at the first insight into my data. And if we continue discussion, which was based on computation in Microsoft Excel sheet, we can currently add the first variable into a model. So it means we would add a variable which is differentiating male and female. Before we start, maybe we would discuss about possible expectation. So it means whether male or female would have higher probability or odds for surviving or not. So for which category would be higher probability or odds for survival? For male?
Female?
For female, we expect, as this was also the case in our Microsoft Excel sheet, so we are expecting similar results. So we would take the sex variable. As you can see in this icon, there is small a in the last one circle here, or you can go back and you can see these are only texts. So this is text variable. So JASP can handle also text variable as independent variable in the model for logistic regression. So if you take the sex, click here into the factors, as JASP will not allow you to enter this variable into covariates. So I would move it into the factors, and JASP will recompute our analysis. So I would go here, and as you can see here, there is expression sex, and in brackets you can find male. It means that we are currently comparing male to female, and female, as far as you are familiar with the discussion about dummy variables from linear regression, so female is a reference category. So we are comparing male to female. And we can simply find the value of odds ratio for sex, in brackets male, which is approximately 10, or 10 divided by 1. So maybe that somebody can help me to interpret this value. What is the meaning of this 10 divided by 1?
That for male to die is 10 times higher.
And what is higher, probability or odd?
Odd.
Yeah, as it is odds ratio, so it is the ratio of odds. So for male, there is 10 times higher odd to die in comparison with female. Once again, odds to die means ratio of probability to die versus to survive. So once again, repetition of these previous concepts. And so only instead of 8 divided by 1, which was the case in our Microsoft Excel computation. So real life figure is approximately 10 divided by 1. So that's the interpretation of odds ratio for sex, in brackets male. As you can see, if the odds ratio is above 1, it means that our coefficient, once again in scale logit, is about 0. So these values are related. Once again, this 2.3 is logarithm of this value, approximately 10. And what is the inverse function for logarithm? Does anybody know how I can compute this value of odds ratio from this estimate, which is in logarithms? Which function should be applied here? it is called exponential function. So I would take E, which is Euler number, approximately 2.71, etc., etc. And the exponent for this would be this 2.3. So 2.7 over 2.3 is approximately 10. So JESP is currently recomputing these values. So this is odds ratio, or sometimes as it is exponentiated value of this estimate, so sometimes it is called as exponentiated value of estimate or exponentiated value of B. So sometimes you can find in some another packages, instead of odds ratio, XB expression here above this column. So that's the ratio between male and female and between their odds. And maybe that somebody can help us also to interpret intercept currently, at least odds ratio value. What could be the meaning of the intercept currently? We added a new variable, which is differentiating between male and female. So what could be the intercept meaning currently? For which category this is the odds of non-surviving versus surviving, 0.5?
For male.
For male.
So it should.
Why for male?
Because we switched the coding.
We didn't switch coding for male. Male is here the category for which we are computing. So if I would rephrase it, so male is 1 and female is 0, I would call it here. Yeah, we change categories here. So it means here I am computing for non-surviving, but for non-surviving of female or male?
Female.
Female. Once again, if you go back into the logic of intercept in linear regression, every time the meaning of the intercept, if we added some independence, is it is the average level of the phenomenon for all of those who have zeros for all independence. And 0 for independence means here that it is female. So ratio of non-surviving and surviving female means it is 0.5. If you can check it by figures, so we can go into frequencies, contingency tables, and we can here define a contingency table with the sex as rows and survived as columns. And here in cells, we can ask for row percentages. And here you can see very easily that for female, proportion of survived, yes and no, is 2/3 divided by 1/3, or 2 divided by 1. Or in other words, for non-surviving, 1/3 divided by 2/3, and 1 divided by 2 is equal 0.5. So it means this is the value of this odds ratio for the intercept. That's 0.5. And if I take the fraction here for male and female, so it means this 1 divided by 2, and this is, I guess, 5 divided by 1. So if I recompute 5 divided by 1 and 1 divided by 2, I would get approximately 10 divided by 1, which is this value of odds ratio for male. So, in other words, currently, this first insight into the logistic regression is nothing more than only descriptive statistics, which is the same as contingency tables. So here, 0.5 means that if I reverse it, once again, for easier interpretation, that 2 times more women survive than didn't survive. Is it understandable or not? Do you have any questions related to this first description of my data? Okay, so it seems it's clear. So once again, the meaning of the intercept is odds ratio or odd only for the category which is according to the all independence at 0. So currently it is odd for female. So once again, 2 times more women survived in comparison with those who didn't survive. And for male, the situation is 10 times worse than for women. So in other words, if I would ask you that you would compute odds ratio for non-surviving for male, what would be the value? What would be odd for male to non-survive? Is anybody able to compute it? It would be
0.25.
No. It would be 0.5 multiplied by 10. That's one option. What is the value 0.5 multiplied by 10?
5.
Yeah, approximately 5 divided by 1. It means 5 more men didn't survive in comparison with those who survived. Or another trick would be, once again, to go back to our data matrix. And we can reverse the codes for sex. I guess by double click. Oh, it's not possible. Yeah, no, it's not only responding. So wait a minute. And if we double click here, and I would change the order of these categories. So here, female would be the category for which we will be computing coefficient, and for male, it will be a reference category. So it means constant or intercept will be computed for male. So here it is. Chess will recompute result for us. And here we can see that the odd for male is 5. And for female, it's logic. It's just reciprocal value of previous 10 divided by 1 is 1 divided by 10. So these are correct computations. So I would once again reverse categories. So maybe it was better to see positive values. So once again, male would be our category for which we will be computing coefficient, and female will be a reference category. So I would close it. And we would go back to our computation, and we will move forward to another results. So here it is. So once again, 0.5. Once again, the value for female, and for male, the situation is 10 times worse. So that's about odds ratio and their meaning. And odds ratio are usually the most important coefficients for us in logistic regression. Once again, we usually do not use original estimates, which are using logit scale. Okay. Next, what we can add to this model. So I will make a copy of this original model. Maybe first of all, I will only change original model to only intercept to save original model. So intercept only model. So here for this model, I will replace sex, and I will use this as the model for gender. Gender as no. Currently, not copy of descriptive statistics. Sorry for that. So once again, I will copy this, and here I would add sex as factor. So here it is, and I will type gender as factor. Okay, so that's the next model. And our new model will add some more predictor. So I will type it. And I would propose currently that we would add the second variable, which is age, and it would be cover rate, as it is continuous variable. So here's title, and I would take age and move to cover rate window. So I would be applying model for survival, non-survival, based on sex and age. We have discussed previously about the impact of age on survival. So we are currently expecting that age, if it is increasing, survival is decreasing, or as we are currently modeling not surviving, so not surviving will be increasing by age. So I would move age as cover rate, and our new results will be available in a few seconds. So here it is. And here we can see recomputed results. So previous results were comparing male and female. The value of odds ratio was approximately 10, currently slightly increased to 11.8. There is new coefficient for age. We will be discussing it briefly in a few minutes. And there is also new intercept. Previously, intercept was approximately 0.5, and the meaning was the ratio of not surviving versus surviving for female. What could be the meaning of the current intercept 0.271? Is there some idea what could be the meaning of this current intercept? For which category this odds ratio of non-surviving versus surviving is valid?
For female passenger.
Okay. With the age of? How old female has the odds ratio for non-surviving 0.271?
Young female.
Young means? What is the current age? So once again, if I would like to interpret intercept, I need to include zeros in all independents. So 0 for age means it is newborn female. Yeah? So this is odds ratio for newborn female. So it means that most of these newborn children that were girls would survive on Titanic, in other words, as the ratio of non-survival and survival is 0.271. So it means if I make reverse ratio, so it would be approximately, I guess, 4 divided by 1. Probability to survive is 4 times higher than not survive for these newborn girls. So that's the meaning of the intercept. The meaning for the sex is nearly the same as for previous case. So for male, the situation is approximately 12 times worse than for female. Only I should add some more comment. If you remember our discussion about multiple regression versus simple regression, maybe somebody can help me to interpret this coefficient more precisely. So what I should add to the interpretation that this is comparison of male and female. What should be added about the impact of age?
Maybe we should find an average age of passenger.
Sorry, I cannot hear you.
Maybe we should center this variable.
No. Centering is not necessary. Maybe for age 0 is still possible. But if I would like, yeah.
That the older you get, your chances to die increase?
I'm not currently discussing about this coefficient. I am discussing about this coefficient formula, and I would like to hear what is the difference in the meaning of this coefficient. This is also slightly different figure from previous one. So currently I'm discussing about difference for male and female if I control the impact of age, yeah? So as age is included in my model, so currently this is the net impact of gender, and age is not somehow influencing this coefficient. So I would like to say that this is the net impact of gender if I control the impact of age, as age is here included. Okay, and now I would give you a space and you can try to interpret this age coefficient, odds ratio. So what can be the interpretation of this age odds ratio? I guess that somebody tried, so if you can repeat it. So what could be the meaning of this 1.006 odds ratio for age? So let's try somebody, please. Nobody would try.
The age doesn't impact your chances to survive.
That age is?
Is not impacting your chances to survive.
And you can recognize this from this value. So you mean that it is close to 1, so there is no impact?
Yes.
Okay, it can be maybe the first interpretation, but I would say it is not maybe fully correct. We will discuss about it. Okay, some other opinions? Okay, so I would add some comments. Let's go to the logic of this age variable. We can check, of course, this scale by descriptive statistics, but my expectation is that there are some newborn kids on Titanic data file, and there are maybe also people approximately 8 years old. So this is quite long scale. And for these long scales, I guess that we discuss this topic also during linear regression cases. It is usually not quite easy to interpret the logic such as if the age is increasing by 1 unit, it means you are 1 year older. So our odds ratio of not surviving, as once again we are modeling not surviving, is increasing by 1.0006. So if there is long scale, usually these estimates in logarithms are close to 0, and these odds ratio are close to 1, but it doesn't mean technically there is no impact. It means only that it is not quite wise strategy to interpret these coefficients by 1 unit change. So, for example, for the age variable, instead of 1 unit change, we can apply different, or let's call it more units than 1 year. What would be your proposal to apply such change? 10 years, 20 years, 30 years, why is it so to apply such different units such as 10, 20, or 30. Do you have some idea why we would apply more than only 1 year change? So, for example, if you're studying demography, we are discussing about generations or cohorts. And what is usually one generation or one cohort? What is the year distance for one generation or one cohort?
30 years.
Yeah, 20 to 30 years. And that's why usually for the interpretation of the age in such models as we have here, maybe the 20 or 30 would be maybe better. So I would propose for simplicity to take 20 years for computation. Unfortunately, usually in statistical packages, and JESP is not exception here, there is no direct option to implement 20 years in this age variable. So it means JESP will not automatically compute this coefficient. So I would show you how to do it. I would be using Microsoft Excel environment for this computation. So there are two options. First one, I guess maybe slightly easier, is to take this odds ratio. So it means 1,0,0,0,6. So I have this odds ratio here in Microsoft Excel environment. And if I would like to find odds ratio not for 1 year increase, but for example for 20 years increase, so it is quite easy. You would take 1,0,0,6, and you must take the 20th power of this 1,0,0,6. So I would compute it. So 1,0,0,6, this symbol is for power in Microsoft Excel environment, this hat, and you would type 20, and here is odds ratio for the difference of people who are 20 years older with those who have some current age. So currently it is not too close to 1, but it is slightly bigger. So it means 1.12 is the odd for those who are older 20 years in comparison with those who are younger. So this is first possibility. If I would like, for example, to compare the oldest and the youngest people in our data, so I guess that the difference is approximately 80 years. So I would make the 80th power, so 1,0,0,6 and the 80th power. And the ratio for the oldest and for the youngest is 1.6. So these are options how we can recompute odds ratio by some more units than only 1 unit change, which is present here. So this is one option. Second option would be to take original coefficient 0.006. So I would use it once again here. So this 0.006. And I must remember once again that this is logarithm of this value, or in other words, if I would like to compute once again odds ratio, I must exponentiate this value. And if I would like to compute 20-year difference, so first of all, I must multiply 20 times the 0.006 and then exponentiate. So I would use once again Microsoft Excel, exponentiated function exp, and in brackets, I need to type, it should be 20 times by 0.06. So here is the link to 0.06, the end of bracket, and once again, 1.12. Only you can see there is small difference between these two values, as these values are slightly round up. So this is a slight imprecise computation, second one, but approximately 13 is the odds ratio for older people by 20 years in comparison with younger people. So it is not truly 0, but the impact of age is not huge, especially if I compare it to the impact of sex, which was impressive, approximately 12 times higher chance to survive for female or 12 times higher chance to not survive for male. So that's the interpretation. So once again, brief recap. The meaning of the intercept is odd for newborn girls. Age, usually we do not use original coefficient, but we use some units for continuous scale, such as for age, it could be 20 years or something like this. So I would take 20th power of this value or 20 times by this value exponentiated. And for male versus female, interpretation is very easy. I would only compare male with female category, and I am currently modeling not surviving. So for male is odd for not survive 12 times higher. So that's age and sex as one continuous variable and one binary variable. And the last one type of variable that can be present in logistic regression model.
Sorry, I have a question, Professor.
Yeah, of course.
But if we broke down age into like made it categorical variable,
yeah,
would it be possible to I don't know, to analyze it?
Of course, it would be possible to analyze it only if I would prepare a categorical variable for age. It wouldn't be here in covariates. It would be here in factors, and there would be maybe more categories. So I would need to prepare dummy variables, or as you will see in a few minutes, Jess will do it for us. So I will have more coefficients. So we will do nearly the same stuff with class on Titanic in a few minutes.
Okay, thank you.
Okay, only I would like maybe to add one more comment, and thanks for this question. This is a very important question. If the impact of age is the same for all the scale, so I would use this variable as continuous, as we are currently using here. But if I, for example, know that quite a lot of, for example, newborn children were dying on Titanic, and also old people were dying, but people in the middle age were not dying, it would be quite good strategy to prepare categories and to use these categories into the model. So first of all, maybe it would be good to try to prepare some categories for the age and compare it to survive and not survive variable. And if the impact is quite linear, then use original, so it means continuous variable. If not, then use categories. Okay, so last one variable we will introduce into our model is class. There are three classes in my data, first one, second one, and the third one. Once again, first one was for the best people, and last one, the third one was for poor people. So before we start computation, we expect that those who were in the first class were surviving more probable in comparison with those on second class, and also those on second class maybe survived more probable in comparison with those who were in the third class. So first of all, I will make a copy of this model. So once again, I will only once again change title. So gender and class will be as factors and age as covariate. So I will take this class and move it to factors. So in a few seconds, once again, I would get results. And here it is, and I can see as in my data, there were three classes. So the first class is omitted here. So it means that this coefficient for second class is comparison of the second class versus we omitted the first class. And the next one probability, next one coefficient for third class is once again comparison of the third class in comparison with omitted the first class only. Before we start to discuss about these two coefficients, it means especially about these odds ratios, this is maybe once again necessary to repeat the meaning of the intercept. So what is current meaning of the intercept 0.023?
The ratios for newborn females of first class.
Yeah, definitely correct. So it is newborn, H is 0, female, as it is not male, and it is not included category first class, so it is newborn girls that were in the first class on Titanic. So as you can see, this odds ratio is even lower than previously. Previously, this was only for female. Here it is. And now it is maybe 10 times lower. So if you were newborn girl, which was in the first class on Titanic, so it was nearly sure that you would survive, in other words. Okay, so that's odds ratio. The meaning of age and interpretation of age is nearly the same as previously, so we wouldn't discuss about it. Also, for gender differences, we wouldn't discuss. And we would briefly discuss about these two variables. So once again, we have originally 3 categories, first, second, and the third class. And that's why we are applying, or JESP is applying automatically only 2 of these. JESP automatically will omit the first category. If we would like to change it, but there is nearly no reason currently, I would go once again to data matrix. I would click here into P-class variable, and I would change settings. So it means ordering of categories, and my reference category can be different. But here I wouldn't propose to make some changes, as here we have values above 1, and that's what we usually would like to see in logistic regression for easy interpretation. So 3.6 and 12.5 approximately. So I hope that once again somebody can help me to interpret this value. So what is the meaning of 3.5 and 12.5 approximately?
People from second class have a 3.56 higher chance of odds ratio of non-survival as compared to the first class, whereas the third class has a 12 times higher chance of not surviving,
okay,
as compared to first class.
If you compare these values, thanks a lot, to previously computed value for difference of male and female, so it seems that gender, as well as if you are in the third class versus first class, it is nearly the same importance. So your situation should be very bad if you are male, and also should be very bad if you are in the third class. Last one question related to this table is if somebody can help me and if he or she can say what could be the odds ratio, not third versus the first, second versus the first, but third versus the second. What could be the comparison of the third class and second class by odds ratio not surviving? Are there any ideas how we can compute such figure?
Maybe 3 divided by 12.
We can take this ratio and divide it by this ratio. So it is approximately 4, if I'm computing it very roughly in my head. So if I would compare third class and the second class, it would be this divided by this. Why is it so? As it is third by the first one and second by the first one. So if I make the fraction of these two, first one class will be omitted out from this computation, and it will be only third to second. If you don't believe me, of course, you can go back to data matrix and you can change the order of classes on Titanic, and you can take the second class as the first one category, and you will get two coefficients for third and the first one, and it will be approximately 4 odds ratio for the third class currently. So this is not necessary. Once again, you can take one coefficient divided by the second, and you would get odds ratio for these two classes. So we have covered so far discussion about different types of variables. So you know how to use binary variable, nominal or ordinal variable with more than two categories, and also continuous variable. So we have covered all necessary points that can be present in my data. I would make only a short comment about last one possibility that could be present in logistic regression, but we wouldn't go into detail. As far as you know from linear regression, we can also combine variables together. How we call these combinations of variables together? Does anybody know?
Interactions?
Yeah, these are interactions, correct. So also in this type of regression, it means logistic regression, we can combine these variables together. For example, if I would combine age and sex, I would try to find whether the relationship between age and survival or non-survival is different for male and female. It is quite easy to apply such interaction in chess. As far as you know from linear regression, you would visit model option, and here you would take, for example, age and sex and move it forward. And I guess that in a few seconds, chess will recompute and will give you the result for this interaction. For example, here, this interaction, age multiplied by sex, is not too big, but it seems that slightly more is increasing the impact for age for male than for female. As for female, this is the original odds ratio, and it seems for female there is no impact of age. It is about zero for logits and about 1 for odds ratios. So maybe that
can you please do that again with the interaction variable, because I think my chess is broken probably. How did you do that?
How to prepare interaction? Okay, so I will move it back. So I will take first one variable, clicking left button on my mouse, then click on control button on my keyboard, and then once again clicking on the left button on my mouse to sex. And move these together to...
okay. Okay. Thank you.
Okay, once again, brief substantive interpretation, but I'm not forcing you to use interactions in logistic regression, and this is not quite common, but still here, the impact of age, which is for women, is nearly no impact at all. And it seems that previously defined effect for age is present only for female, as this coefficient is nearly the same as previously found coefficient for male. So it seems that for male and female, the impact of age is slightly different. So that's first insight by this interaction. But once again, I'm not forcing you to apply interactions. Also in your homework, it's not necessary for you to apply interactions into logistic regression model. Okay, so that's all for this. I would call it introductory example of logistic regression in jest. And once again, we were discussing about the example of Titanic. And before we start to discuss about logistic regression in more detail, maybe I would like to ask you one question. So Titanic disaster, of course, it's not something pleasant, and we are sorry for that. All the human mankind is sorry for that. But still, this is some special occasion. And if we are discussing in quantitative methodology about populations and sampling, we are trying usually to take sample and then infer our results from the sample to the whole population. And that's why we are using confidence intervals, statistical tests, and other tools. So the question is, if we are currently discussing and computing with Titanic data, is it sample or is it population? Should we somehow infer from Titanic data to some bigger population or not? So if somebody can try to answer, it would be nice from you.
I think that we are analyzing like population of Titanic.
Yeah. The Titanic seems, at least to me, and I hope that at least for some of you, as population data. So according to my opinion, and I'm convinced about this for statistical reasons, our results we have just covered were descriptive statistics of the situation of Titanic. So we have covered estimates, or mostly odds ratio, as descriptive statistics. So there were no space, of course, Chess will offer for us, for some testing or even confidence intervals. They are present here in statistics. You can ask for confidence intervals. But here on Titanic data, there is no space for this generalization, as we are discussing about the whole population and we are describing this population. So currently, we are using logistic regression as descriptive tool, I would call it. But of course, that mostly we are using samples and we are inferring from samples to the whole population. So of course, that for the next analysis, we will be using tools such as tests, confidence intervals, etc., etc. So I would briefly skip into the presentation. So some basic information about binary logistic regression. So if you like to read some text about logistic regression, so I would propose that one of the best texts, it is something like classical reading in logistic regression, is the book which was published in Wiley by Hosmer and Lemeshow, called Applied Logistic Regression. I guess there is also a newer version than these two editions that are present here. Long Scott published also a very good book which is called Regression Models for Categorical and Limited Data. And quite small book, but also quite good for the first introduction, is Fred Pempel, Logistic Regression and Primer. If you would like to be expert in the field of categorical data analysis, you must definitely read Agreste. I would call it Categorical Data Bible, which is called Categorical Data Analysis, consisting of more than 700 pages. In Czech, we have quite nice title, which was published in Czech Sociological Review, and in English, the title would be "Don't Be Afraid of Logistic Regression." For Czech students, I can recommend this article. And if you would like to apply logistic regression in SPSS, here are two recommended titles from Andy Field and Marian Rushes. So if we go to general description, so we can apply three different models in logistic regression. For binary variable, we call it binary logistic regression, and we have covered basics, and we would go further today and next week. There are also models for ordinal and nominal variables. Unfortunately, JESP is not capable of these, but I will show you only a brief example of nominal so-called Polytomous logistic regression case in SPSS, and also next time we will once again skip into M+ package. So I will show you that M+ is capable of all these models. It means for nominal, ordinal, binary variables. JESP is capable only of binary variables. We will only briefly discuss at the end of presentation next time about closed techniques, so I would skip this discussion to the next week. If we are discussing about binary logistic regression, only brief recap. Once again, we are moving from original variables to probabilities, odds ratio, and logits. And classical equation for logistic regression is based on logit of the left-hand side, and then impact of the intercept and individual independent variables, the same style as for linear regression. So we can also add interactions, we can also add dummy variables. So once again, nearly the same step as for linear regression, as we covered also on Titanic data. And basic questions that we would like to ask in data that are sampled to the whole population are following. The first question is whether my model fit to my data. Once again, for linear regression, the question was answered by overall F-test and R-squared. In logistic regression, there would be something what would be called as a likelihood ratio test. Some packages, but the JESP is not offering this test. So some packages also offer so-called Hosmer-Lemeshow test. And instead of R-squared, we would follow something what is called pseudo R-squared. So it means some similar coefficients, but as R-squared is based on variance, and for binary variable, it is not possible to define variance. That's why we call these coefficients as pseudo R-squared. We also know that in linear regression, we try to evaluate the importance of individual variables. So it means we are applying t-tests, beta coefficients, etc. For binary logistic regression, it would be similar, only instead of t-test, we would be applying Wolf's test, and standardized coefficients are present here as well. The last question is whether my data fulfill some assumptions. So for example, for linear regression, there is linear relationship between independence and dependence. For logistic regression, there should be linear relationship between independence variables and logit. It is only slightly complicated to discover, so that's why we will not cover this topic in this introductory lectures about logistic regression. Here, I would like to inform you that the estimation of coefficients in logistic regression is not based on ordinal least squares. Instead, we are applying a maximum likelihood technique, which is the most common technique for most of advanced statistical techniques. And unfortunately, there is no special formula into which you should include your data, and it will give you results, but you must recompute many times. We call these repeated steps as iterations. So that's why we are not capable to compute logistic regression without computer. And now we will briefly introduce, and next time we will continue this discussion, our real life data examples. And my main goal here in this real life data example would be to prepare the model for usage or non-usage of internet. We will be using World Internet Project 2006 data from the Czech Republic. So first of all, if you can open in JESP data that are called INET. So here it is in my case. So you should have this data matrix. There is age, gender, education, using or non-using internet. This will be our dependent variable. Then there is a number of people in the household above, I guess, total number of people above 18 and below 18. These are DOM1, DOM2, DOM3. This is information about income of the family. and the last one variable is about the size of the village or city in which the respondent is living. So this is my data file. This data file consists of more than 1,000 of cases. Here is the last one. So it is nearly 1,600 cases. And once again, the variable in which we are interested in, which will be our dependent variable, is whether I am using or non-using internet. So there are two options, yes and no. Before we start to prepare some preliminary model, and we will finish our discussion next time, I would like to ask you about individual possible predictors. So we would go through age up to the size, and we would discuss whether these variables should have an impact on usage or non-usage of internet. I would like only to add once again that these data are approximately 15 years old, so we must go slightly back into the history of the Czech Republic and internet coverage. And let's start with the age variable. Is it possible that the age will be somehow influencing usage of the internet or not? What's your opinion? Should we include age into our model or not?
I think yes.
Okay. And if I say yes, I expect that older will be more probably non-users and younger will be users, I guess. Yeah? Am I right? Okay, thanks a lot. So what about the gender inclusion? Were there any differences, and once again, 15 years back in the Czech history, between male and female in internet usage or not, and why?
If there was a difference between female and male users,
okay.
15 years back.
Okay, expectation. What about the impact of education? There are 4 codes, I guess, here from elementary up to tertiary.
It will impact.
Okay, so we will use education as well. So we will skip use, of course. Now it is the number of people in the household in total, number of people in the household which are below 18 years, above 18 years. So my question is whether some of these variables can somehow influence whether the respondent, which is randomly selected from the household, should be used or not.
Maybe my hypothesis is that the more people are, or the families with more people in a household will use internet more often as they can learn from each other, but we will see.
Okay, so I would maybe propose for the first insight to leave these variables out, so not to include. Okay, then the next one variable, which is family income. Is there some expectation about the impact of family income on usage or non-usage of internet?
Definitely, like if family is affluent, then the chance that this family uses internet is higher.
Okay. Only I would like to warn that for family income, as you can see also in the first screen, there are some decays. So maybe some values, there is no information about income. And as these decays are present in my data quite frequently, it means that if these values will be omitted, also these all cases will be omitted from my analysis, and maybe that my analysis will be biased. We will discuss this topic next time in more detail. And the last one variable is size of the village or city. Should we include this variable or not?
I would include it. I suppose the larger, the higher probability of usage.
Okay, at least if you go back 15 years ago in the Czech Republic, there was huge difference between the coverage of the internet in small villages and big cities. Nearly for all big cities, the internet was everywhere and was quite cheap, but especially for small villages, there was no option or options that were very, very expensive. So we need to take into account also this information. Okay, thanks a lot for this first yeah. Some question? Okay. So for the first insight into my data, I would propose that we would only take this variable of internet usage and non-usage. So I would click into descriptives. And I would check this variable of usage. I maybe also ask for frequency table. So we can see that in my data, there is bigger proportion of users, 55%, in comparison with non-users, 45%. So it seems that the proportion of users is slightly higher than non-users. And also second information should be added here. And once again, if we go back into Titanic data example, we know that if we wouldn't change it, so by default, we would model the second category in my data. It means non-using versus using. So if you would like to change it, we would go into data matrix and change order of the categories of dependent variable. Of course, that we should also check all the rest variables present in my data, but it's not necessary currently. I can guarantee that I checked data previously, and if there were some problems, I fixed it. So now we can go very quickly enter into the first computation of logistic regression, and next time we will continue this example. So here I would close the descriptive statistics dialog, and we would enter into regression, logistic regression. And the first, what I would propose is to take only use variable, and we would only compute intercept. So it means this is only model with no independence. I would ask also in statistics for odds ratios. And here we can see that in logics, the estimate of the coefficient is negative. So it means, once again, there is more users than non-users, as no is currently coded as class 1. So we are currently modeling non-users versus users. Odds ratio is 0.8. So once again, if I would take this 44.9 divided by 54.8, I would get this value of odds ratio 0.8. Before we would go further, so it means we would enter some independence. The question is whether we should like to model non-using or whether we would like to model using. So what's your opinion about this topic? Should we reverse the categories of dependent variable to model users, or should we leave as it is, so to model non-users?
I would use users, since it will give us probably positive values. At least for this intercept, you are right. And usually we are interesting in positive categories. So I would go into use. To recap, let's go into no, move upwards. So here it is, and just will recompute the results very quickly. So the estimate in logic is just opposite. Instead of minus, it is plus 0.198, and odds ratio is 1.2. So it means there is approximately 1.2 more users than non-users, or probability of using internet in my data file is 1.2 times higher than probability not using the internet. Maybe I would like only to add here some title. So I will call it
as intercept-only model. First, and I would make a copy once again, and I would add the first variable into my model. So I would make a copy, and I would prepare a model into which I enter the age. So age as covariate. Okay, so here it is. I will take age and move it to covariate window. So here we have results, and before we start to discuss about the impact of age, and then we will add some more results. First of all, we could discuss about the meaning of the intercept. So currently, odds ratio is 31.394. And I would add, to be correct, that if I get my variable age, here I can move it to this descriptive statistics table, that minimum in my data file is 12 years old children and maximum 88-year-old people. This survey was designed to kids as well. That's why there are also 20 years old kids here. And if I go back for my last model, oh, sorry. So if I here can see odds ratio 31.394, we know from previous discussion, it would be odds ratio for using the internet for newborn children. But there are two problems with this interpretation. First one, I do not expect that newborn children are capable of using the internet. That's maybe the first problem. And the second problem is that usually these surveys are designed to adults or maybe some older kids. Currently in our data, the youngest kids are about 12 years old. So interpretation of the intercept currently is not possible. If we would like to change it, once again, repetition from linear regression, we would somehow change the scale of age, such as, for example, we would center the age or recompute the age. So the 0 would be 12, so it means the youngest, and the rest of the variable would be the difference between the youngest and next respondents. But we wouldn't change these settings currently. So currently we know that intercept will not have any substantive important information for us. So we wouldn't interpret intercept for this and next models. So that's about odds ratio for intercept. And now we would like to interpret the importance of age. So here is the value in logits. Here we have the value in odds ratio. And the first of all, I would take this value with negative sign minus 0.076. If we are modeling usage of internet, here is a note, use level, yes, is coded as class 1. So we are modeling odds using versus non-using. So this negative sign means that as the age is increasing, the usage or odds of usage is decreasing. So this is the coefficient which is saying there is negative impact of age. It means if you are older, so there is increasing probability you wouldn't be using the internet. So that's the impact of age by this sign. Here we have odds ratio for this coefficient. So it means exponentiated value of this estimate. So it is slightly below 1. So the same story, negative impact. And once again, if we go back into a previous discussion, somebody can help me how we would interpret this coefficient of odds ratio. So what we should use instead of original odds ratio coefficient.
You can try to use age categories.
We wouldn't try age categories. We still be using age, but we would use change not by 1 unit, 1 year, but maybe once again, for example, 20 years. Yeah?
Yes, I meant that, like 20
okay,
years.
sorry for that. So I would once again take this formula. So I would take once again 20's power for that. So this is 0.927 and 20's power is 0.21. Once again, if I would like to interpret odds or odds ratio, it is usually better if it is below 1 to reverse the value to make reciprocal. So I would take 1 divided this value, and it says that if you are 20 years younger, you have 4.5 times higher odds to using internet, or if you are 20 years older, you have 4.5 times higher odd non-using internet. So it depends which categories you would reverse, as original coefficient is based on odd for using, so it means probability using versus non-using, and currently we are discussing that for age, the value would be 0.2, and the interpretation that the odd to use internet is 0. times higher or lower. It doesn't make any sense in the language. So once again, proposal is make 1 divided by this value and reverse categories of dependent or independent variable. So 4.5 times higher odd for those who are 20 years younger. That's one option, reverse of independent variable, or 4.5 times higher odd of non-using internet instead of using, which was original scale. So this is the age impact. Last comments before we finish today's lecture will be devoted to this variable. And if you can see this coefficient 4.5 for 20-year older or younger people, does it seem substantively significant or not? Is there a big difference between those who are younger or older or not in usage internet according to my data?
I would say yes.
Yeah,
me too.
It's quite impressive. And of course, we should go back on the ground, I would say, and we should tell that all these coefficients, doesn't matter whether it is for 1 year or 20 years, or doesn't matter whether it is currently in a reversal, are valid only for my data. It means for my sample. If I would like to generalize this result, there are 2 options. I would go into statistics and I would ask for confidence interval, and I would ask for confidence interval in odds ratio scale. So here my table is slightly bigger currently. There are 2 new columns, 95 confidence interval for odds ratio scale. And I can see that estimate for my sample was 0.927. That's the figure which I currently try to recompute. But it can be as low as 0.920, or it can be also 0.934. So I would take these 2 values, 0.92 and 0.934. So 0.92 and 0.934. And I would copy these equations. And here we have confidence interval for 20 years old change. So for 20 years change. So currently, for my data, is this 4.5 if I take 20th power and reverse original value. But if I take into account that my data are sample and I would like to generalize to the whole population, it could be as low as approximately 4, but as big as 5.3. But still, it seems to me this is substantively significant result. So it means that age really matters whether people in 2006 in the Czech Republic used or didn't use internet. So that's the first possibility for generalization. So confidence interval and only recomputed for 20 years change.
Can I have a question?
Yeah.
The 20 years change is from the mean of the age or from...
No. That's general description in my model. So it means it is comparison of somebody who is, for example, 10 and 30.
Yeah, so it's 20 years anywhere in the model.
Yeah.
Oh, yeah, okay.
Yeah, thanks for this question. And the last one comment, which will be very, very brief, is related to this Volt test, which is included in 3 columns called Volt statistics, D, F, and P. So it is nearly the same stuff as partial t-test and linear regression. So it means this test is testing whether the variable, it means in an individual independent variables, has impact on dependent variable. Once again, here dependent variable is logit of original variable, etc. So here is test statistic. It is only coefficient divided by standard error, usually squared. So this value divided by this value squared is 365. There is 1 degree of freedom for the Volt test, as this is only one variable, and this is p-value. Null hypothesis says there is no impact at all, and alternative says, okay, this coefficient, it means this estimate in logit, is not 0. And this p-value is very, very low, 0. There are many, many zeros, 80 times 0, and then on the 81st place, after decimal place, there is 1, 9, 7, etc., etc. If I compare it to conventional values such as 0.05, 0.01, or sometimes 0.005, it is still very low. So according to the test, I can say that this result is statistically proven or statistically significant. Sometimes we are using, but once again, I would like to warn you that current recommendation in the literature says that we should avoid to the expression of statistically significant and insignificant. So once again, it seems from this test as well as from this confidence interval, we should discuss about the impact of age on the usage or non-usage of internet, and this is quite important effect. So this is the last information for model today.
Sorry, I have a question, but
question, of course.
Can we then say that our odds ratio is also now